So far in the digital logic series, we've been talking mostly about using gates to implement Boolean expressions and designing circuitry. And then we had a handful of discussions about using more complex devices such as encoder, decoder, multiplexers, and those kinds of devices. In this particular section, we're going to be talking about programmable logic array. As the name, logic devices or PLDs, as the name implies, these logic devices can be programmed to do different things depending on what we need. And the magic and the way this works is through this these fuse systems that are available. For example, when you you could have this kind of fuse, which basically is unchangeable. This is a fixed fuse from the, we say it's fixed in the factory, which means we cannot change it for our circuits. But on the other hand, we have this kind of fuse, which is represented by an X on the junction, and we can either leave it intact or blow it as is shown here. So we remove the X. So if we leave the X, that means the vertical wire is connected to the horizontal wire. If you take it off, that means the vertical wire is not connected to the horizontal wire, which is very useful because this would allow us to customize these devices to the particular application we have for designing our circuitry. A couple of other ideas to talk about before we get into more details of how these programmable devices, what varieties of they exist and how to use them, is kind of understanding the way they're structured. Okay, and some of the shortcuts we take in drawing how they're put together. So let's take a really simple design where we would have simply two inputs coming in. We will have a A1 coming in and an A0 coming in. And typically these devices will have, much like we do the schematic, they do the same thing. They have the inverted line coming in, and they would have the non-inverted input coming in, such as this. So I'm doing two input because it's a very simple, that actually is probably not even available on the market. It's too few inputs. So, and then you will have this line that is drawn to a AND shape. In reality, you will, this one line actually represent four separate lines. Usually it is because we have two input and four possibilities, the non-inverted input and the inverted input, and we might want to make connection to any four of these. They give you four lines, but for simplicity of drawing, they always draw it as a single line. Okay, and then typically there are as many ANDs as there are minterms, typically. So for them, typically we have four of them. So here's one, and typically when we design devices using PLD, we only draw the particular particular gates that we use. Okay, this portion is referred to as an AND array, simply because it looks like an array when you fully draw it out. So that's what it is. For example, if I wanted to design a exclusive OR, for example, I simply will come in, blow everything other than this one, and that's a A0 naught, and then I need A, and then maybe use that line to do the other portion, which is A1 and A0 naught. So what it comes out of here for this one is going to be a, oops, let me put it at the end so this way it doesn't interfere with what I have to draw here. And here we would have an A1 naught, A0, and this line would be A1, A0 naught. For this exclusive OR case, most likely I won't even draw these other ones because I'm not going to use them, so there's no point in drawing them. Simplify, because sometimes you can have, of course, n inputs, so you have 2 to the n rows. You don't want to draw all of them if you don't use them. So that's an AND array, and then you may have a bunch of OR arrays. Again, we draw a single line, but you can assume there is enough line to connect to every one of those horizontal lines as they're coming in. So the AND the AND is creating the products, and these OR arrays, these are OR down here. And these OR arrays are what's used to actually create the output. In our case, let's say for an exclusive OR, I only have one output, so I don't need to use the rest of them. So if I'm not using the rest of them, but I won't even draw them if right there. And so the only one I have is here, and that's my function, and my function happened to be A1 not A0, or that's what I'm looking for, A1 A0 not. So all I do, there's a fuse here and there's a fuse here. Now what I've shown here, it shows that both the AND array, and this piece is called the OR array, of course, because there's ORs. Okay, so what I've shown here is actually a PLA, because it allows you to change the fuses on both sides. We actually have three distinct type of PLDs out there. One is called the PROM, and the distinction of PROM is that all the AND arrays are fixed at the factory, and customers can only deal with OR arrays. So in other words, all of these are made in factory and we can't change them, but the only one we can change is decide to either use it or not. Okay, let's go ahead and take a look at a kind of a general PROM and see what it look like. This is a general PROM. It's got N input, A0 to AN, when we typically draw it this way. Now, you do not have a choice on this. When it comes from the factory, the first AND group will bring out the M0. So it's going to be A0 not, A1 not, on and on. The second one is going to be second midterm 1, which means only A0 is not inverted. And the last one in the list would be M to the power of N plus 1 minus 1, so which would be basically all ones here. Okay, and you may have M output as well. I don't know how many, but however many outputs you need, you can have. And but on the OR array, you have an option of either leaving this intact or getting it out. Okay, so the only programming ability you have of customization, programming is customization, is how you would deal with an OR array. So that's called a PROM. The other option you have is a PLA. The PLA is by far the most flexible one, because you can change both sides of this equation, both the OR array and the AND array, both can be changed. Both this, you can decide which fuses are connected here and which fuses are connected on the other side. That's the most flexible. With flexibility comes the bigger devices, more expensive, take more power and all of that, but they're sure easy to design with, because it's pretty easy to make whatever expression is given to you, you just do it. It's pretty easy. Now this last one is called PLAs. I'm sorry, PALs. PLAs are the flexible one. They're called PALs, which stands for Programmable Array Logic, or sometimes also called GAL, Generic Array Logics. And these guys are kind of customized. They're somewhere, so they're not as flexible as PLA, not as rigid as PROM. So they're somewhere in the middle of those two. And they typically are put together based on if there's a lot of people for certain application that need some level of flexibility, but not full flexibility, they might make it. Here's an example of one. As you can see in this one, the AND array is completely programmable. You can do it, and then the output can be fed back into the input to do more complex things. But as far as the ORing part is concerned, you're relatively limited in how many. For this one, only allows you to OR 2 products that you can create based on the line. So it's a bit, it's kind of an oddball. If you need it, it's great to have it, but you got to have a certain application that lends itself to it. Okay. So that's it. So we got basically, let's kind of bring all of this together. You've literally got 3 kinds. You've got the PROM, and the distinction is that the AND array can only be programmed at the factory. You can't change it. OR arrays you can change. And then we have the PLA, programmable logic arrays, which are flexible on both ends. You can change both both the OR array and the AND array in these things. And then finally, this customized version of that, which is called PAL or GAL. So let's go ahead and take a look at an expression and see if we can implement it. So we have this expression given. So first of all, it's 3 input. So and they want us to so when they say implement a function using PLA, what they're asking for you is to do the the fuse diagram for it. Once you've done the fuse diagram, that can be entered into the programmer device that comes with these things, and it will program it exactly like you want. So let's go ahead and take a look at it. This one to me look like is 3 inputs and 1 output. So I'm gonna select a 3 input, 1 output PLA. So I know PLAs are both programmable, both the AND array is programmable as well as the OR array. So I'm going to have basically one that brings in A2. Of course, each one of these will have an inversion and will have itself. I'll make it long enough. And then I'm going to have A1. And then I will have A0. Okay, I'm only going to draw the AND arrays I need. So I know I'm going to need a few of them. So there's going to be an AND here. How many terms do I have? I have 1 term, 2 term, 3 term, 4 terms. So I at least need 4 of them. How many ANDs are there? There's going to be, because this is 3 inputs, there is going to be 2 to the power of 3, which is 8 AND gates typically, but I'm not going to draw all of them because I don't need them. And I only have 1 output, so my OR array is going to have 1 output coming out, and this is my F coming out. Now remember, we draw this one line, but in reality it's many lines ANDed together. The same here. This we draw as one line, but it's many lines that can be individually connected to the output of the AND to get our function figured out. So this would be, I'm doing a PLA, and so all I need to do is go ahead and take a look at this input and say, okay, that input is got, the first term is A2 naught, A1 naught, and A0 naught. So here is A2 naught, A0 naught, and I'm sorry, A1 naught and A0 naught. So this term is actually giving me the A2 naught, A1 naught, and A0 naught. Okay, and I'm going to use it to put the OR. Okay, and then the second term is going to be A2 naught, A1, and A0 naught. So that gives me the term A2 naught, A1, A0 naught. The next term is, look at the next term doesn't have A2, so I don't do anything with A2. I'm only connecting A1 and A0, and that's my answer. Okay, and then finally, the last item we have to do is the last term, which is A2 naught, A1 naught, and A0. So A2 naught, A1 naught, A0. By the way, I'm writing these mostly for your benefit or our benefit, so you just know what I'm doing here. And then when we put the fuse, do not blow these fuses so they're intact. I've got my function, which is an OR of all these terms. Okay, so that was fuse diagram for PLA, the most flexible and the easiest one to work on. Now, the next thing I got to do in step 2 was to design this thing using PROM. Oops. Using PROM. Now the problem with PROM is that the inputs the AND array is fixed. An AND array is completely fixed and I cannot do anything with it. All I know is that I have all the min term. So all I have to figure out now is which minterms are 1. Once I know that, the problem is solved. So what's the best way of knowing what are the minterms? The best way and the easiest way to figure this out is to do a truth table. So we have A2, A1, A0, and then the function here. And so we're gonna do the truth table 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, so the first term is telling us that everything is 0, function is 1. Second term is telling us if it's, that's basically a 2, it's a 1. And then this term is saying, I don't care what A2 is, as long as A1 and A0 are 1, it's a 1. So this would be a 1, this would be a 1. And then the last one says if A2 is 0, A1 is 0, and A2 is 0, A1 is 0, and A0 is 1, then we're good. So that will be here. And the rest are 0. Okay, so I have minterm 0, minterm 1, minterm 2, minterm 3, and minterm 7. So we're gonna same idea as we've done before. We've got A2 and its inversion, A1 and its inversion, and A0, or I should have been small letter, but oh well. Okay, and I have 1, 2, 3, 4, 5 minterm, and these, so I'm going to draw all of them for now, but remember you don't have to do that. So since I have 3 input, I'm going to have 8 minterm, right? So I'll just draw the whole thing, because I want to make sure you see that it's got all the minterm going through it. And they are fixed at the factory, so we have no control over changing them. So we've got 1, 2, 3, 4, 5, 6, 7, and 8. So you start basically just like the truth table. This is gonna give me M0. This is gonna give me M1, M2, M3, M4, M5, M6, and M7. And they come from factory just figured to do that. So you're gonna have, notice that I'm using a different kind of things for my fuse map, and this is the fuse map for the PROM. And then 1, notice how I connected to a 0, and then we'll have that was 0, 1, 2, and 3. Okay, now we go 4. Okay, well, let's see all this. I'm sorry, 1, all this. So, and then so here is 0. Then we've got 1. Then we've got 2. And then we've got 3. Okay, so that's created. Now on this side we'll have an order array. Since we only have 1 output, that's it. And now we're gonna say, okay, it needs to be M0 or M0 ORed with M1, with M2, with M3. 1, 2, 3, 4. Okay, so we've done that, and then the last one is this. Notice how the fuse is connected, and here's my F. Okay, so these are the 2 we really need to use. That you can also do that if you choose to. The last one is doing one of these, and all you need to do is you need to. Sometimes you can do it, sometimes you can. That's a little more complicated. You gotta find the right pal or gal to do the work for you, but you will have these kinds of configurations to work work with. So for example, let me just do one. So for the third case, which was PAL, you have some of the flexibility we had before. So what's going to happen is that you have to make sure you have picked a PAL which at least have enough terms that you can OR with each other to get the job done. So if you don't have that, for example, the one shown here won't be able to do the work for you. Okay, but let's say if you had one that potentially had how many terms do we have here? 1, 2, 3, 4 terms. If you were able to find one that had four of these coming through, then you would be able to implement it much like you did with the PAL. Okay, PLA. So what you would do, you would connect the appropriate one to this to get an output. So that would be the PAL. Okay. So getting back to here, these are great devices to have because it allows us to customize a single hardware to the particular application that we have. PROM, the AND array is fixed at the factory, or is completely up to you. You can do that in the field, meaning as you're using it, you can customize it. PLA, you can customize both sides, most flexible probably, and more expensive probably per connection. And then some mix of the two, but the mix of the two doesn't work for all applications. You have to find one that has enough ORs or ANDs as you need it to get the job done, where the PLA and PROMs are completely flexible. You pretty much can build anything you want out of them. That brings us to the end of programmable logic devices.